Today I'd like to discuss with you something called the chi-squared distribution, and then we'll also do an example where we use the chi-squared distribution to perform what's called a chi-squared goodness of fit test. Okay, this is a picture of the chi-squared distribution table. It's in the back of many statistics textbooks. This specific one you're looking at comes from the back of the reference guide that comes with the AP exam and AP statistics. Okay, so if you look at the picture at the top, first thing you'll notice is that this distribution is skewed right. Okay, and you should make a note of that the chi-squared distribution is always skewed right, no matter what. So it's never quite really a normal distribution. If you think about other tables where we saw degrees of freedom column, if you look over here on the left, degrees of freedom, you'll notice that next to the degrees of freedom, like say degrees of freedom 1, you'll see these numbers here, but then if you go down to degrees of freedom 10, you see different numbers. So that sort of implies that the distribution we're looking at changes shape depending on degrees of freedom. Now you've seen that before, let me just remind you, in the t-chart, or the t-distribution, which is what we're looking at here. So the t-distribution had that property, but we knew that as the degrees of freedom went up and the t-distribution, as df got bigger, then the t-distribution got closer to the normal distribution. Okay? So a fair question might be, does that happen here? Well, like I said before, the chi-squared distribution is always skewed right, so it'll never actually be the normal distribution. But let's take a look at what happens as the degrees of freedom increases. So we're going to go to our calculator, and we'll go to y equals. Okay? Now you'll notice here I have chi-squared PDF. You can find that in your own calculator by doing second distributions. What I'm going to do here is set this to a low degrees of freedom. So let's just say 6 degrees of freedom. And let's graph it and see what it looks like. So here we go. Okay? And you'll notice that that picture you're looking at looks a lot like this picture. It's skewed right, and most of the distribution, the area is over to the left. But let's see what happens if we increase the degrees of freedom. So I'll go back to y equals, and I'll go over to where that 6 is, and let's make it something like 30. Okay, close parenthesis. Enter, graph, and here we go. Oh wow, and surprise, surprise, this distribution is starting to look a little bit more like a normal distribution. Okay, it's not exactly, it's still skewed right, but it's closer. So that sort of gives you a sense of how the chi-squared distribution changes as the degrees of freedom increase. All right, so just like all distributions, when you want to use them, you care about what's called the test statistic. So in this particular distribution, the chi-squared test statistic is equal to, let's just make a note of this, this is the test statistic, is equal to the sum of the following. You take your observed counts minus your expected counts, and you square that, and you divide it by the expected counts. And there's going to be more than one of these. There's going to be quite a few of these. And that's what this is telling us to do, is sum up all the different chi-squared statistics. All right, so that might not make a lot of sense to you right now, but if we do an example, this will become clearer. Okay, so let's try and do an example and see if we can use the chi-squared test distribution. All right, so it turns out that M&Ms, the candy that you eat, the company that makes it, M&M Mars, used to promise the following. They used to say that 24% of all the M&Ms they make are blue, and then they'd say that 14% of all the M&Ms they make are brown, and so forth. They made this promise that you're reading about on the top. Okay. So what I did is I went out and bought a bag of M&Ms that you might get like at the candy store or something like that, and I counted up how many of them were in the bag of each color. So the first thing I counted up, I noticed that there was 12 green, 4 blue, 6 red, and 8 yellow. So that's what these numbers are telling us. And then in total, I had 54 M&Ms in the bag. Okay. So the question then is as follows. Is this a surprising result? Does this match up with the promise that M&M Mars made? Okay. So these numbers are called my observed counts. That's what these numbers are. So let's make a note of this. These are my observed counts. And you'll notice observed counts, that's part of our chi-squared test statistic. So there's our chi-squared test statistic again. Here it is. Here's the first part of it. Okay? So we need to get our expected counts. Well, our expected counts, a little bit of common sense, and you know what we need to do. We had 54 M&Ms in this bag, because that's what happened when I added them all up. We expected 24% of them to be blue. So what we can do now is figure out what was supposed to happen. So we can do, for example, the expected blue. Well, actually, let's go to a new page. We'll take this with us. We'll copy it. Okay, go to a new page here. We'll paste it. And we had n equals 54 M&Ms in total. So our expected counts would be as follows. We would do 24%, or 0.24, times 54. And then we would do 0.14 times 54. Okay? And this would be the expected blues. And this would be the expected browns. And we have to go and do that for all the colors. So here's green. Green should be 0.16 times 54. And then we had orange. And orange should be 0.2 times 54. And you can see what I'm doing. So then red, bear with me for a second while I just write these things down. And then yellow. Okay? So maybe after I calculate these, I'll be better equipped to answer the question, were my observed counts surprising or not? Like, for example, I'm noticing that there's only 4 blue in this bag of 54. We were expecting 24% of the bag to be blue. So this might be a surprising result. Okay, so next thing we're going to do is calculate all these things. Well, I've done that for you, so let me tell you what the answers are. So this first one is 12.96. This expected number was 7.56. Here was 8.64. And then these over here are, this was 10.8. And over here we have 7.02. And over here we have 7.56. So now we get a little bit better sense. For example, if you notice, look at blues for a minute. We were expecting about 12.96 blues, and our observed count was only 4 blues. So that's pretty far away, okay? But some of the other ones, maybe not so much. So let's see. For green, we were expecting 8.64, and for green, we had 12. So that's only 3 away. Let's look at the other ones. So yellow was 8, and yellow here was 7.56. So those weren't far away at all. Okay. It's time to calculate the chi-squared test statistic. So to do that, remember what we've got to do here. We've got to do every observed value minus every expected value. We've got to square that and divide by the expected. So I'm going to use my calculator to speed up this process. Oh, and then let's not forget, when we're done with that, we've got to add them all up. Okay? So here we go. In the calculator, we're going to go to Stat, Edit, and we're going to take the time to type in all of these numbers. Okay? All right. So you notice those magically appeared there. I just paused and typed them in. Now, I was very careful when I typed them in. So here's what I mean. For example, the first thing I typed in, L3, was the observed counts of blue. And that means in L4, the first thing that has to go there is the expected counts of blue. So you can't just put these, oh no, I'm sorry, that's green, forgive me. You have to type them in the correct order. These are the blues. We had 4 blues we observed. We were expecting 12.96. Okay, so all of these match up. So you need to look carefully. There were 6 red, and if you look at this information, we expect 7.02 red. And if I go to my calculator, 6 and 7.02 are next to each other. Okay, so now we're ready to get that chi-squared test statistic, and here's how you do it. We're going to go to the top of list 5. We're going to do open parenthesis, and we're going to recall, hey, wait a minute, I put my observed in list 3. So I'm going to do the observed first, second list 3, or second 3, minus my expecteds, which are in list 4, so second list 4. Then I'm going to close the parenthesis and square that. So that's observed minus expected squared. I'm going to divide by the expected, which were in list 4. So I do second 4, and there we go. I hit enter, and here are all my different chi-squared test statistic. Notice that second one of 6.19. I shouldn't be surprised that that's really big, and that's because that was the blue. We only got 4 blue, and we were expecting looked like almost, well, 13, 12.96. Okay, last thing we're going to do, just don't forget what we got to do here. We have to add them all up or sum them up, so we're going to do that in the calculator. We do second quit to get out of this. Okay, we'll hit clear. And do the following. Do second stat, which takes you to list. Go over to math, and go to number 5, which is the sum. Okay, and our chi-square test statistics, I might have forgot where they were. If you forgot, go back to stat edit for a minute, like I did. Where did I put them? I put them in list 5. There they are. There's all my chi-square test statistic. Okay, so I'll do second quit to get back. And I'll do, over here next to the sum, I'll do second 5, hit enter, and there is my total chi-squared test statistic. It's 11.593. Okay. It's 11.593. Okay, now, it's sort of strange here. We sort of stepped up to, it feels like we're doing a significance test, and we are. The only problem is with a significance test, you really do want to have hypotheses, so we should mention those right now. All right, so here's how you write hypotheses in the chi-squared way. HO is that the distribution of M&Ms, well, I'll say M&M colors, is as promised. In other words, M&M's Mars made a promise to give the following. Where are they? Here they are, 24% blue, 14% brown, and so forth. You could write all of that in the HO if you like. Okay? The HA is simply that the distribution of M&M colors is not as promised. So these are the two hypotheses we're testing. Okay? And we're actually almost there, because now that we have chi-squared, it's almost time to use the chi-squared distribution table. Okay? There's only one problem. When I look at that chi-squared distribution table, and I know my chi-squared, in this case, chi-squared was equal to 11.593. The question is, where do I go looking in this table? And just like the t-distribution, remember, here's the t-distribution, the degrees of freedom mattered. You had to look at the degrees of freedom you have. Now, in the t-distribution, it was always the sample size minus 1, or in the case of a two-sample t-test, you did n1, you did n1 minus 1 and n2 minus 1, and then you took the minimum of those. So that's how you used the t-distribution table. A similar thing happens here. The only thing is it's not really n minus 1. The degrees of freedom in the goodness of fit test is the number of categories minus 1. So in our case, there were 6 categories of color. So the degrees of freedom is 6 minus 1, or 5. Okay, so what we do is we go to the 5th row, 5th degrees of freedom, there we go, and we look across until we find our chi-squared test statistic. So let's go looking for it. Well, I look across, I get 11.07, so that's pretty close, and then the next number after that is 12.83. So what you notice is we don't actually get our chi-squared test statistic, but we have 2 chi-squared test statistics that is between. And then you finish up by noticing, hey, look, there's a tail area that goes with this. This tail area is 0.05, and that tail area is 0.025. Well, there you go. Now you're done. Now you know our p-value. Oops, that should say our. P-value is between, we can say, it's less than 0.05, right? But it's greater than 0.025, because that's the 2 tail areas that we just got in our table. So using the famous using alpha equals 0.05, we can say our chi-squared test statistic is significant. Okay? And we can go on. I'm not going to write it all, but we have enough evidence to reject HO in favor of HA. And we can say that based on our sample, the distribution of M&M colors is not as promised. So I got a significant result here. Okay? Now, we'll finish up by just saying, what are the assumptions that go with this? All our significance tests have assumptions. So this test would have had them also. Okay? So really, you should check these before you get started. My goal today was just to get you comfortable with chi-squared first, and then we'll go back and say, hey, what about all those other things we need to do? All right, so this is a goodness of fit test. Number 1, you need to make sure that all your data are counts. All that means is, for example, our data were counts because we had exactly 12 greens or 4 blues or 6 reds. You wouldn't do a chi-squared goodness of fit test if you had things like percentages or decimals or proportions or things like that. Okay? So that's number one. Okay. So here we are. Data are counts. So that's number one. The second thing you want to make sure is that you had an SRS. Okay? Now I made an assumption here that this one bag of M&Ms I got represented a fair SRS, and some people might be critical of that and say that that's not really true. But for the time being, we just assume that. All right? And then always that your sample size, has to be less than or equal to, or I should say 10 times your sample size, is less than or equal to the population. Well, we only had 54 M&Ms, and I'm sure there's more than 540 M&Ms in the world. Okay? And then the last thing you need to check is that all expected counts are greater than or equal to 5. Okay? Well, in our case, if you look at our expected counts, here they are. They were all decimals, but not all of them were greater than 5. So we luck out in that case. Now, it will be, sometimes you'll look at a chi-squared problem and you'll notice that all the counts are not greater than 5. Some textbooks will say no more than 20% of expected counts. Okay, less than or equal to 5. So in other words, they'll say 20% of your counts, expected counts, could be less than 5, but no more than that. Okay? So these are the assumptions you need to check. And once they were satisfied, which they were in this case, then it was safe to proceed with this test and conclude what we concluded. Okay? So that's how you do a chi-squared goodness of fit test. Goodness of fit meaning that M&Rs made a promise about a certain percentage we should expect, and how well did our sample fit, or how good a job did our sample do fitting against what was promised to us. Okay? Well, more tests to come with related chi-squares. Thanks for watching.